is basically from lecture 1 up to lecture 5, which is the material that we're going to start covering today. Okay, so you will see problems regarding about sample space, events, counting sample outcomes, the probability of an event, how to compute the probability, and also the new material for today. So, any questions so far? Again, don't wait until the last minute to start studying for the exam. These concepts that you are learning look simple, but when you start practicing, you see that involve a lot of details. So it's important for you to get familiar with those details and try to solve as many problems as possible. The more you practice, the better you will understand the concept and the better you will perform in the exam. Also, if you have questions, please stop by my office, send me an email. If you are not able to see me during my office hours, send me an email and I'm going to try to schedule a different time to meet with you. Okay, so last time we started discussing the probability topic. We talked about the probability of an event. But before we discuss the probability of an event, I listed those theorems that I believe are more important for your understanding of the concepts in terms of sample space, how to count the number of outcomes in a sample space, and also in a particular event. So those theorems that are listed in this slide are very important. So we covered part of this material. We talk about the probability and some of the properties of a probability. And we highlighted these three. We know that the probability of an event is to be between 0 and 1. No probability should be greater than 1. So if you find a probability that is greater than 1, that you're doing something wrong. And the summation of all the outcomes, or the probability of the sample space, is always equals to 1. Okay? We discussed several examples, and we also talked about the additive rule for probabilities, and specifically about the union of two events. We used some Venn diagrams to represent the summation of two events and how the summation of two events or the union of two events are computed. So if you have some overlapping, you need to account for that overlapping by subtracting once the intersection of the two events. But you know that when you have mutually exclusive events, you don't have to account for the intersection because those events are independent. So in such a case, just add the probability of both events. And you can extend the same approach or the same concept to more than two events, which is the case represented here. For 3 events, we can apply the additive rule, but in this case, you have to sum the intersection of the 3 events. And we discussed several problems, and I believe that was the last problem we discussed, okay, in which we were looking at the probability of a specific event by looking at the complement and also by looking at the union of events. So today we're going to start with a new topic, which is called conditional probability. Okay? The independence and the product rule. But more important is the conditional probability. So the probability of an event B, let's call it B, occurring when it is known that some other event A has occurred, is called a conditional probability. So now we are looking at conditions. So if we know the probability of an event, we can predict, or we want to know what will be the effect of that event into this new event. Here we are calling event B, occurring when we know that some event A has occurred. Okay, so that's why we call it conditional, because we know something already happened. So based on that fact, what is the probability that this other event will happen? Okay, and we have some definition for such type of problem. So the conditional probability of B, given that event A already happened, is denoted by this notation. So we're going to use the probability of that event, given that A happened, is defined by this notation. So we look at the division of the intersection of the events divided by the probability of that event that occurred. Okay, and that event or that probability of event A is always greater than 0. So let's look at this problem, see how we can apply those concepts. So in this problem we have the probability that a regularly scheduled flight departs on time is given by this event, call it PD. So it's 0.83, and the probability that it arrives on time is 0.82. And the probability that it departs and arrives on time is given by this intersection of events, and is 0.78. So now we're interested in two different things. First one is to find the probability that a plane arrives on time given that it departed on time. So if we know that it departed on time, or that's the given fact, we want to know if that happened, what will be the probability that it also arrives on time. So what do? Let me write those probabilities here. So the probability of departing on time is 0.83. Probability of arriving on time is 0.82, and the intersection of the two is 0.78. So again, this is a conditional probability. So the first item, probability that arrives on time, this word right here is very important. Given that it departed on time, we need to find that probability. So the notation that we use is the probability. This line right here means given. What is the event that is given? Departed on time. So given that it departed on time, we want to find the probability that it arrives on time. So using the definition, so by definition 2.10, we know that that probability is given by the probability of the intersection of the events divided by the probability of D. So that is 0.78 divided by 0.83. And that's 0.94. Okay, so given that it departed on time, the probability that it arrives on time is 0.94. Now let's look at part B. Now we're looking at the opposite. So what would be the probability that the airplane departed on time given that it has arrived on time? So here we use the same notation, but in this case is the probability departing on time given that it has arrived on time. So using the same definition, we have the intersection of the events divided by the probability of arriving on time. So this is 0.78 divided by 0.82, and this is 0.95. Yes, sir.
If it's asking for predicate parts, I use probably the 0.83.
Point B, the probability that departing on time given that it has arrived on time. So remember, you have historical information, and you're using that information to come up with these probabilities. 0.83, 0.82, 0.78. That is based on your historical data. Now, using that historical data, you're trying to make some predictions. So these are predictions. So what you're saying is, let's say that based on the information that I have, the probability that I have that the plane will arrive on time, given that it departed on time, is going to be this. So it's not like the plane already arrived. You see what I'm trying to say? We're using the historical information to make some predictions. So based on those two events, we want to know, okay, so if in this airport, given that if the airplanes depart on time with this probability, then the probability that if the airplane arrive on time with this probability, then the probability that they depart on time is this. Okay? So that can help you out in planning, let's say, for your airplane schedules and so on. Okay? That answer your question?
No. Because I was asking why are we using PD instead of PA for the bottom number for the A?
For A?
Yeah.
Oh!
It looks like it's asking
Let's go back here. So that's based only on the definition of the conditional probability. So the event that is given is always the denominator. Okay? So,
this is kind of counter.
yes. Well, somehow. But we are just using the definition. And I can derive these expressions, but for the purpose of this class, it will not make sense. So I'm just providing you with the definition. But we can discuss that later. It will make more sense. Okay? Any other questions? Okay, good. So make sure that you follow the definition. So always remember that the given fact is denominator. And that's why here, departed on time is that given event. So we use the probability of D as the denominator, same thing here. Okay, so now let's talk about independence. So the independence of two events, they are independent if one event has no impact on the occurrence of the other event. Okay, and that makes sense, right? They're independent, there's no effect on one to the other. So two events are A and B are independent only if the conditional probability is always equal to the probability of the event that you're trying to compute. So in this case, the probability of B given A is always equal to the probability of B. That means that those two events are independent. They have no effect one into the other. Same thing with the opposite probability of A given B. If it's going to be equal to the probability of A, that means that there's no effect of event B on event A. So those events are independent. Okay? Now, let's talk about the product rule. That enables us to calculate the probability that two events will both occur. Okay, so basically what we're doing here is just solving for the intersection of the events. So if you move the denominator of the previous expression to the right, then you'll get the product rule. So if in an experiment the events of A and B can be both occur, then the probability of the intersection is given by the probability of one of the events given times the probability of, or the conditional probability of the two events. We can also write the intersection of A and B as the intersection of B and A. It's going to be the same. And the only thing that is going to be different is the events that you have in your expression. So that's the product rule. We can apply that product rule in our next problem. So suppose that we have a fuse box containing 20 fuses, of which 5 are defective. If 2 of them are selected at random and removed from the box succession without replacing the first, what is the probability that both are defective? So we have some numbers here that we can use to compute some probabilities. So if we choose one from the box, think about it. What will be the probability of that one being a defective fuse based on those numbers? 5/20, that's correct. And what will be the probability of the second one being defective? Say that again. Correct. So now it's not straightforward because we don't know if the first one was defective or not. So we need to take into account that event in order to compute the probability of the second one. Okay, so the probability of the first fuse effective equals the probability of A, which is 5/20, and this is 1/4. But the probability of the second one is conditioned to the first one being defective. So the probability of B given A is 4/19. So if the first one is defective, then we know that the second one has the probability of 4/19 to be defective. So the probability of both being defective, we know that conditional probability is the probability of B given A equals the probability of A, the intersection of B given the probability of A. So the probability of the intersection is equal to probability of A times the probability of B given A, and that is 1/4 times 4/19, which is 476, 1/19. So let me see if you're following. So based on those events, we get, the question is what is the probability that both of them are defective? So the first one, easy, right? You know that's 5 defective over 20, that's 1/4. Okay, no question asked. Now the second one, the probability that the second one is defective is going to depend on the first one is defective. So that is a conditional probability. And we know that if the first one is defective, then we're going to have only 4 defective items remaining in our group. And we already got one out of the group, so that makes our total equal to 90. So if the first one is defective, then the probability that the second one is defective is given by this. Okay, so now we need to use that information to compute the probability of both being defective. Okay, so we need to combine these two events. So the probability of both being defective is the intersection of the events. Remember the Venn diagram, you're looking for the overlapping between the two events. The only way that we can compute that is using the product rule that we discussed here. So the intersection of the event equals this expression. We have that information from our problem. So the only thing that we need to multiply is these two numbers to get that probability. Okay, so the intersection of the events, product rule, we get the information we need from the problem, and we can compute that probability. In this case is 1 over 90, which is kind of low, very low. And you should expect to have that type of probability, okay, for this type of problem. Any questions? Okay. So the product rule, one more time. This is for the case in which we have two events that are mutually exclusive or independent. They are independent if and only if the intersection of the two events equals the probability of one times the probability of the other. Therefore, to obtain the probability that two independent events will occur, we just multiply the two individual probabilities. And here's an example for such a case. So we have a small town that has one fire engine and one ambulance available for emergencies. So right away you know that one is coming from, both of these vehicles are independent in terms of their location and the service that they provide. So the probability that the fire engine is available when needed is 0.98, and the probability that the ambulance is available when called is 0.92. In the event of an injury resulting from a burning building, find the probability that both the ambulance and the fire engine will be available, assuming that they operate independently. So the problem actually is telling you that the events are independent. So what would you do to find that probability?
Multiply probabilities.
Correct. So the events are independent. So based on our discussion here, if they are independent, the intersection of the event that both of them are available is just the multiplication of those two events. So in that case, we just find the intersection of the events is the probability of A times the probability of B. It's 0.98 times 0.92. And this is 0.9016. So next we have a very interesting problem, especially for those of you who are in the electrical engineering program. So this is the first example where you can apply probability to a electrical engineering problem. Can I move to the next slide? So here we have an electrical system that consists of 4 components. And the system works if components A and B work. So these are 2 components that are in series. So A and B needs to work. And either of the components C or D works. So in order for the system to work, these 2, A and B, need to work, but only one of these 2 needs to work. Which makes sense, right? Because if this is current, you can go this way or you can go this way. Okay? So the reliability is a concept that you're gonna, especially if you're in the industrial engineering program, you're gonna hear a lot. Is the probability of the system working. So the reliability of each component is also shown in the figure. So we have the probability that this system will work, or each component will work. So it's 0.9, 0.9, 0.8, and 0.8. And you want to find the probability that the entire system works. So any ideas for solving this first part? This is A. So for the entire system to work, we need to make sure that this component is working, this component is working, and one of these two components is working. Any concept from the course that you can apply? So let's say we are looking at Venn diagrams, and these are 3 events. Say A, B, C. Let's say we have only 3 components. So if we want to make sure that all the 3 are working, we need to find the intersection of the 3 events, right? So that's what we need to compute here. We need to find that intersection of events. So if you put that into probabilities, that means that you're looking at the probability of A intersection probability of B, and the intersection of the probability of C union D. And why we're looking at the union? Because it could be one or the other. Okay? Doesn't have to be C, it could be C or D. That makes sense? Yes, sir. Yes. Yeah, we're looking at A first. Well, there are two different problems. The first one is just in general, the entire system to work. That means that one of these two components needs to work. And these two have to work, and one of these two needs to work. No, not each individual. Okay? But in that case, I will make things easier because you just look at the intersection of the 4 and you find that probability. But in this case, it's just the function, the entire system to work. And that's why you need to make sure that these two are working and one of the two from the parallel. So, first thing we have to do, we have the probability of A, we have the probability of B. Yes, sir.
You will find your analogous part B because it's saying either or, like you can see what these can work and they have the same probability of working. So wouldn't that be a good way to do that?
Say that again.
Since C and D have the same probability,
Yes.
wouldn't if one of them didn't, if one of C or D didn't work, it would be the part of it.
So if one of them doesn't work,
That would give us what the equation would be. If it's either or, it's not.
so again, when you look at the union of events, you're basically looking at the entire area. Okay, so that will give you more chances of the system to work. If you just look at one of them independently, then you're removing a big part of the chances that you have for the system to work. So that having that extra item or component there is basically increasing the chances of the reliability of the system. That makes sense? Yes. If you have only one, then basically you're removing this entire area for the system to perform, right? So that's why we have two components that basically is covering, say we know that this component is more prone to hitting or failing, even though we have those numbers. But we want to make sure that that particular area of the system is covered, so we add an extra component. Okay? So, based on that expression, and again, we're going to discuss B, we have this probability and this probability, but we don't have this. So we need to find out a way to get that information. So we know that the probability of C union D equals the probability of C plus the probability of D minus the probability of C intersection D. Okay? And by theorem 2.11, independence, we know that the probability of C intersection D is going to be equal to the probability of C times the probability of D, which is 0.64, 0.8, point. Because we know those two components are independent. The performance of one of them is not determined by the performance of the other. So the probability of C union D equals 0.8 plus 0.8 minus 0.64, and that equals 0.96. So the probability of A intersection, the probability of B intersection, the probability of C union D equals 0.9 times 0.9 times 0.96, and that is equal to 0.778. Questions? So we needed to apply several concepts one more time. Concept of independence, by looking at the system, you know the performance of one is not dependent on the other, they are independent. So we can apply this rule for the intersection that we need here. So it's a multiplication of those components, probabilities, 0.64. So using this intersection, now we can find the union because we have this information, and this information, and then we can solve. So the reliability of this system is 0.78, around 0.78. Now let's look at part B. Component C does not work given that the entire system works. So this is a conditional probability. And again, we are assuming that 4 components work independent. And if we were to treat them and we know that component C does not work, we need to make sure that this one is working in order for the system to work. So if let's say we want to find the probability that all the components are working and component C is not working, what would you do? Multiply the probabilities of all of them, but for C you need to do something different. You need to look at the complement, because that's the probability of D working. So the complement, 0.2, is the probability that the component is not going to work. So let me put this here. So B is going to be the probability of A intersection B intersection the complement of C and the intersection of D. But this problem also provides a condition, which is given that the probability of the system works. So that is equal to 0.9 times 0.9, 0.2 times 0.8 divided by, correct, the probability that the entire system works. We already computed that here. So it's 0.778. And that is equal to 0.111661. Questions? And again, very important problem. Go back, review this problem. Make sure that you understand what we are doing. If you don't understand what we are doing, stop by my office or send me an email or try to contact me. I will explain it to you. Yes.
I'm sorry, don't we use a different, would we use something different than 0.778, because that's the probability of A, B, C, and then B working, but for part B, it's given the C does not work.
That's a really good question. And the thing is, when we're solving this problem, we are using historical data. We don't know if component B or D is going to be working or not. That's the thing with this conditional probability.
So we could just use like 0.9 times 0.9 times 0.8, and just assume this is not working. That's what it says in the first part.
The first part?
Where it says component C does not work. So if you're just if C does not work, then you still.
So if C is not working, if you remove this portion of the question and you just solve component C does not work, you know that the probability that C is not working is 0.2. That's by looking at the complement, right? Now, you want to know what is the chances or what are the probabilities that the system works given that that one is not working. You still have a chance for working because the probability of not working is 0.2. Remember, we are using probabilities. We don't know the fact, or we don't know what's going to happen. So the only information that we have is that with 0.2 probability, that 0.2% or 2% has the 20% probability that that component is not going to work, right? So if you want to solve only this part without this given, the only thing that you have to do is multiplication of this. Okay? That's the answer. That's the probability that the system is going to work based on C not working. Now, when we have a given information, we have that given, we know the probability that the entire system is going to work is based on our observations and based on our experiments, the probability that the entire system is going to work is this one. Then we can add that extra fact to our problem and to our experiment and find out what would be the probability of this.
In this problem, A and B are actually, they actually are on the right, but this is the currency, it just assumes that they're all independent. Like, in A and B are actually, or B is dependent on A, but B, right? Is that what the series is?
Well, they are independent in terms of their reliability. What that means is the failure of this component is not going to affect the failure of that component. So in that sense, the problem is telling you that they are all independent. Okay? For both A and B. Okay? Any other questions? Good. So that was a good problem. And that product rule that we discussed can be extended to multiple, to more than 2 events situations, like we did for the previous problem. You just have to make sure that you follow the proper multiplication of events. Okay, so here we have another exercise. This is a different, and we're going to discuss this problem, and after this problem, we're going to have a lab. So again, ask questions, because the next problem is for you to work in groups. So this problem is the manufacturer of a blue back sign is concerned about the quality of its blue zero. Batches of this element are processed by 3 different departments having rejection rates of 0.10, 0.08, and 0.12. The inspection by the 3 departments are sequential and independent. So the first question is, let me put those events here. So if we call department A, B, and C, so the probability of A complement equals 0.10, probability of B complement equals 0.08, and the probability of C complement equals 0.12. So I'm using the complement to denote rejection, but it's not, I mean, you don't have to use the complement. You can use probability of A to denote the rejection, and then the probability of acceptance will be the complement. Okay, so don't get confused for the notation. So the first item is, what is the probability that a batch of serums survives the first department inspection but is rejected by the second one? So we know from the problem that the inspections are independent, right? Which means that the inspection of the first department is not going to affect the inspection of the second department. So if they are independent, we are looking at what type of probability for this question. So again, there's no given in this particular question, just asking in general. What is the probability that the batch of serums survives the first department inspection but is rejected by the second department? It will be different if the question say, given that it was rejected by this department.
Would it be the intersection of A and complement?
Correct. So we are looking at the intersection of these two events, and will be A intersection of B complement. So we are trying to see what is the probability of those two events happening. And that's the intersection of the event. So we know that the events are independent, right? So when they are independent, we can just multiply those probabilities. So probability of A times the probability of B complement, that is 0.9 times 0.08, and that is 0.72. Let's look at part B. What is the probability that a batch of serum is rejected by the third department? Just following the same concepts. We have the intersection of A, B, C complement, and they are independent. So the probability of A times the probability of B times the probability of C complement, and this is 0.9 times 0.92 times 0.12, 0.099. Any questions? Okay, so let's on this problem, getting groups. And for this lab, if you're able to work on it, should be very easy. So I'll look at the answers you work with. And depending on the performance, then I will decide if I ask the lab as the homework or as one. So for this lab, I can tell you that you're going to use the conditional probability. And if you look at the topic, it clearly says that you're going to use the conditional probability. So make sure that you use conditional probability. Denise? Gerald? Joy? Are you? And you look at your homework and you see something that you don't understand, let me know, we can discuss it. Prayer Beth? Louis? Tom? Javier? Beth? Richard? Ryan? We have two, Ryan? Billy? Shelby? Rico? One? Tarana? Mary? All right. That's right. Jane? Here?
I think that's the first.
Andrew? Corey?
Yes.
Brian? Kyle? David?
Yes.
Joel?
Intersection.
Okay, so let's define the events for this problem. So we have the probability of oil change equals probability of A, and that is 0.25. Then we have the probability of oil filter, probability of B, 0.4. And we have the probability of A intersection B with 0.14. Right? So now what you need to do is to find the right expression for A and B. So let's look at the first one. If the oil has to be changed, that is given. What is the probability of a new oil filter is needed? Okay, so the first part is given. Now you need to find the probability of a new filter needed. I think I cannot make it more easy than that. Yeah, I'm gonna give you one more minute to finish. Remember to put your names on the answer sheet. You can start passing your labs. Okay, let's discuss this problem. Okay, so we have the information already on the board. We have the probability of oil change as 0.25. Questions here? Okay. So I have all the labs. Good. So we have the information, the probability of oil change, oil failure, and the intersection of the events. So the first one, again, this is given. We know that the oil has to be changed. And we want to find what is the probability that we need also a new oil filter. So that is the probability of B given A, right? Because this is given, A is given. We need to find what is the probability of this. Okay, so this is equal to P A intersection B given the probability of A, and that is 0.14 divided by 0.25, 0.56. Questions? Okay, part B again. This is given. What is the probability that the oil has to be changed? So this is the probability of A given B, which is P A intersection B divided by the probability of B, 0.14 divided by 0.4, this is 0.35. Questions? Okay, so what is what? And they're wrong. Yeah. Again, I'm going to look at the results, and depending on the performance, I will decide what to do with the lab. I don't want to affect you guys, so these are just problems for you to start thinking about the type of questions that you are going to see in the homework and also in the exam, and also to give you a better understanding of the concept. Okay? So now you understand how the conditional probability works. Okay? Hopefully, you know how to use those. Okay, so that concludes the chapter 2 and also lecture 4, in which we discuss what are random experiments, what is the sample space, what are events, and we also discuss counting sample points, probability of an event. This is the topic that we just discussed with the additive rule and the conditional probability, independence, and the product rule. So expect some homework based on this today, and we also have a couple of minutes to introduce the next topic. Yay! Just gonna give you an idea of what's coming. So we know how to compute probabilities right now. We know how to use the sample space, how to use the events, how to compute the probability based on the problem. We know the importance of probabilities. We know the importance of knowing when an intersection of events is happening and when the union of events are happening, because that affects the way that you compute the probabilities. They're independent, they are not independent. You need to take those concepts into account for the type of problem that you're studying. So now we're going to look at more complex stuff, I will say, because we're going to use all those concepts that you just learned and we're going to add more information. We're going to discuss what a random variable is, and also how to compute probability distribution. So far we talked about probability, we haven't mentioned the term distribution. Now you're going to start seeing what distribution is. So we're still on the second objective for this course, use probability models to describe uncertainty and make decisions. But what are we going to do now is we're going to use the information about probability of an event, and we're going to discuss how to use those to create random variables, in which we need the probability of an event, and we need the concept of sample. And from there, we're going to discuss what is a probability distribution. Because depending on the random variable, depending on the function that describes this random variable, we can create probability distributions. Okay, so I'm getting ahead a little bit. So these are the 4 topics or the outline for this lecture. Concept of a random variable. We're going to discuss what is a discrete probability distribution and what is a continuous probability distribution. Anyone remember what is the difference between discrete and continuous? Discrete is something that you can count. 1, 2, 3, 4, 5, so on. Continuous are more continuous values, right? Like weight, like the measure, the height, okay? The speed. So that's the main difference, and that's important. And we also going to discuss what is the joint probability distribution. So I'm not going to read this right now, but once you start studying for the exam and also of this concept, first you need to go back and read these learning objectives and make sure that you understand what each item of these learning objectives mean and that you understand those concepts. Because this is a summary of what you should learn by the end of this lecture. Okay, so there's some concepts here in blue. That means that those concepts are important. And we're going to go back to this by the end of the lecture. Okay, so let's start by the concept of a random variable. What is a random variable? And I think this is the slide that I showed you already. Statistics is concerned with making inference about populations and population characteristics. So the testing of the number of electronic components is an example of a statistical experiment. So remember, when you look at the number of defective or non-defective, that is a statistical experiment. So let me put that here. Defectives, non-defectives. And again, we are showing the relation between population and sample, and in deductive reasoning, you use probabilities to come up with the best way to sample from the population. And based on the sample, we're going to make some inference using some statistics. So it is often important to allocate a numerical description to an outcome. So far, we've been listing all the outcomes this way. Like, you have 3 components, you want to know what are the chances of having defectives or non-defectives. You're picking 3 components, and these are all the outcomes that you can have based on being defective or non-defective. And this is a problem we discussed already. So this is your sample space, right? If you take a sample from this batch of electronic components, 3 per sample, these are the only outcomes that you can have. Now, one is concerned with the number of defectives that occur. So let's say that's the information that we want to gather from this sample. So each point in the sample space will be assigned a numerical value. It could be 0, it could be 1, 2, or 3, right? Depending on the number of defectives. So this one will be 0, this one will be 1, and so on. This one will be 0. Based on that description, 1, 1, 1, 2, 2, 2, and 3. And that's by giving a numerical description to each outcome of sample space. Okay? These values are random values assumed by the random variable x. So now we are using those outcomes from sample space and we are assigning a value. We are defining a function for each outcome of the sample space. So in this case, the function is if you're going to add 1 if you have a defect. So using that function, we can describe a random variable. Using the same sample, we can describe another random variable. Instead of looking at the defective, we can look at the non-defective. So in that case, instead of this number being 0, this will be 3, 2, 2, 2, 1, 1, 1, and 0. Same sample space, different random variable, different value. Okay, so these values are random values assumed by the random variable. And that random variable is something that you are defining. Okay? The next slide. So a random variable is a function that associates a real number with each element in the sample space. And that is what we just did for that sample space. Okay? So we shall use a capital letter, X, for instance, to denote the random variable, and its corresponding small letter, X, in this case, for one of its values. And this is the last example that we're going to discuss today. Say we have 2 balls are drawn in succession without replacement from a urn containing 4 red, 3 blacks. The possible outcomes and the values y of the random variable y, where y is the number of red balls, are. So again, we're sampling from these 2 at a time, and this is the sample space. It will be 2 red and 1 black and 1 red, or 2 blacks. If we assign a value to this random variable, number of reds, then we can easily come up with a number for this sample space. So if both reds, this is 2, this is 1, 1, and 0. Does that make sense? Just say yes, it makes sense, right? Okay, so we're going to stop here, and then on Monday, we're going to continue on this one.
I have a quick question.